Today, we're going to talk about a technology that is literally stretching what's possible in space. We're swapping out that old-school heavy metal for a new frontier that's surprisingly strong and elastic. So let me ask you a question. How do you fit a 3-story building inside a rocket? It sounds like a riddle, right? Some kind of impossible engineering puzzle. But believe it or not, the answer is about to completely change how we live and work beyond our planet. You see, for more than 60 years, ever since we first started going to space, our biggest dreams have been kind of squished by this thing called the tyranny of the rocket equation. Now, what that basically means is that every single pound you want to launch into orbit costs a fortune in fuel. It makes everything incredibly expensive, and it limits us by weight and, this is the crucial part, by the physical size of a rocket's nose cone.
So here's how we're going to break it down. First, we'll look at what's called the ship-in-a-bottle problem. Then, we'll explore this new elastic future. We'll get into how something soft can actually be incredibly strong, look at what this means for going beyond Earth, and finally wrap up with the wild new space economy that this is creating.
Okay, so first up, the ship-in-a-bottle problem. This is really the heart of the challenge of building anything big in space. You have to design every single component to fit inside that protective cone on top of the rocket, the fairing, which has a totally fixed and rigid size.
I mean, just look at the International Space Station. It's an absolute marvel of engineering, no question. But it also perfectly shows the old way of doing things, launching dozens and dozens of these small metal cans and then painstakingly piecing them all together in orbit. It took years, and the cost was, well, astronomical.
So, that brings us to the next big idea, an elastic future. If the bottle itself is the problem, what if the ship inside could be folded up? It's such an elegant solution, right? Habitats that launch packed down into a tight little bundle and then just expand once they get to space.
And here's where the math just completely flips on its head. With the old rigid modules, you're looking at a super high launch weight and a really high cost for not a lot of space. Inflatables change that whole equation. Way less weight, way lower cost, and a massive amount of volume.
Just think about this for a second. For the exact same launch, you get 5 times the living and working space. That's enough room for dedicated science labs, factories in space, or even the very first hotels off-world. This isn't just a small step up, it's a total game changer for the economics of space.
But that leads to the obvious question, right? Are these things actually safe? So in this section, How Soft is Strong, we're going to tackle that common idea that these are just fragile space balloons waiting for a tiny rock to pop them. The reality is, they're way tougher than you think.
You know, the language here really matters. The engineers who build these, they don't call them inflatables. They call them soft-shell, multi-layered pressure vessels. Yeah, it's a mouthful, I know. But it really gets to the heart of what they are, a complex, highly engineered system built for survival.
So how on earth does it work? Well, it's all about the layers. It starts with an inner bladder that's totally airtight. Wrapped around that is the muscle, a layer of this stuff called Vectran, which is literally twice as strong as Kevlar. That's what takes all the structural load. Then you have a shield made of ceramic fabrics that basically shreds any tiny space debris. And finally, an outer skin of thermal blankets to protect from the crazy temperature swings up there.
And this tech has been put through its paces for decades. It actually started as a NASA project back in the 90s. When that got canceled, an entrepreneur bought up the patents and actually launched 2 successful test modules on his own. But the real proof, the final validation, came in 2016 when the beam module was attached to the International Space Station, where, by the way, it's still operating perfectly today.
All right, so the technology is proven. It works near Earth. Now let's talk about why it's absolutely essential if we're serious about going further. In this section, Beyond Earth Orbit, we're going to see how this tech is the key to our future in deep space.
Now, here's one of the most amazing and kind of counterintuitive benefits: radiation shielding. See, when those dangerous cosmic rays from deep space hit an aluminum wall, they can shatter and create a shower of secondary radiation inside the habitat. But the hydrogen-rich fabrics in these soft-shell modules are way better at just absorbing that energy, which means more protection for astronauts on those long trips to the Moon and Mars. This is what makes those big, ambitious bases we've always dreamed about actually possible. Just picture it. You land a single compact module on the Moon, inflate it, and then just cover it with a few feet of lunar soil. Boom. You've got near-perfect protection from radiation and meteorites. You could create huge, interconnected communities underground. And you know, this isn't just for NASA anymore, not by a long shot. Section 5, the new space economy, shows how this technology is becoming the literal foundation for a whole new era of business in orbit.
So, the International Space Station is scheduled for retirement around 2030, but that doesn't mean we're just going to abandon low Earth orbit. No way. Instead, the private sector is in a race to build its successors. And guess what? They're almost all based on these expandable designs.
This has just unleashed a whole new ecosystem of ideas. You've got Aerospace designing these massive 3-story habitats. Axiom is building a commercial wing for the ISS that's later going to detach and become its own private station. And a company called VAST is even planning to create artificial gravity by rotating these things. They're like the new Lego bricks for building an orbit.
When you put it all together, you get this amazing positive feedback loop. Lower costs mean more volume and faster deployment, and that opens the door to space for smaller countries, for universities, for individual researchers, all the people who are completely priced out before. It's effectively democratizing access to orbit.
And all this kind of brings us to a final thought. For so long, we've pictured our future in space as this rigid, metallic, heavy thing. But it's turning out that the path forward is actually soft and light and adaptable. It really makes you wonder, if our homes among the stars are going to be made of fabric, what else about our future is way more flexible than we think it is right now?